And this is actually my third time of recording this video, because every time I finish my conclusion, I realize it's just not correct. And yeah, this is my fourth time. And here is the question that I'll be addressing. Why is standard electrode potential positive for reduced electrodes but negative for oxidized electrodes? So before I actually dive into this, just want to quickly say my conclusion is that every science question requires physics in order to understand what's actually happening. So yeah, please study physics well, and please understand physics well. Just don't zone out during your lessons. And yeah, let's move on to the standard reduction potential, also called the standard electrode potential. This is represented by the table I have over here. Why is it called the standard reduction potential, you may ask? Well, this is because if you look at the table, they only contain half equations that are reduction reactions because reduction is gain of electron, and you see all of those reactions, they gain electrons. So yeah, we have positive electrode potentials and negative electrode potentials. And for the more positive the values are, the more stable the electrode is. The more negative the values are, the more reactive the electrodes. And I won't be diving into further why they are stable or why they're reactive. My question solely is, why does the electrodes that reduces themselves positive, why do they produce a positive value for the potential, and why does the ones that oxidize themselves have a negative value? So just a heads up, how does these values actually, how are they produced? So how does scientists come up with these values in the first place? So they will do this kind of experiment where they connect one standard hydrogen electrode, actually I should draw a H here, with another electrode that they want to test, and they will connect them together in what we call a galvanic cell. And here is our voltmeter. So from this voltmeter reading, we can see the value, whether it's positive or negative. And hence this is what we record over here, Okay, anyways, that was a pretty bad and oversimplified explanation, but since you probably know how this works, I'll just skip ahead to the two situations that I've created. One, we're going to compare the standard hydrogen electrode with zinc. The second, we're going to compare the hydrogen electrode with copper. And here we're following the CIE convention, which is basically left hand side being always negative, right hand side being always positive. Well, what that actually means is that the left hand side will always have the anode, the right hand side will always have the cathode. And it's the same over here as well. Okay, now let's start. So for the first scenario, we have hydrogen and zinc. I placed zinc on my left hand side because zinc is the one that is going to oxide itself, and hydrogen is on the right hand side because hydrogen reduces itself. So based on that information, so we know that zinc has more electrons, and the electrons, they will travel from a higher density to a lower density. So in this direction. And to be specific, they will go from the zinc to the hydrogen electrode and across the salt bridge like this to form a complete circuit. Like this. So here I'll label this will be the direction of electron traveling, and if you recall GCSE physics, the current travel direction, so basically the direction of conventional current, that will be the opposite of the direction of electron. So this will be the direction of conventional current. So I'll just quickly label the one down here as well. For this, it is the same. This will be the electron traveling direction, and this will be the current's direction. Now, why is this important? So, if you recall what the conventional current actually means, well, basically the old scientists, they're saying that the protons are what is traveling inside a circuit. So basically we have positive charges, aka protons, traveling from the positive terminal to the negative terminal, which is totally not the case. Oops, did I just draw a lot of things? Okay, sorry. Which is totally not the case, but it's how people back in the days think about electricity. But I just want to bring out this concept, which you will know if you study A-level physics. And yeah, I know you do study A-level physics, so just now we were talking about standard electrode potentials. That's basically electrode potentials, but in a different word. So basically, okay, so from my understanding, the standard electrode potential is just the electric potential, but for electrodes, if that makes sense. And what are electric potentials? This is a reminder that it is the work done to move a positive test charge from blah 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 to blah blah blah. Well, a positive test charge, that could mean a proton, right? And what does a current move? Also a proton, from the positive to the negative terminal. So now the question to ask yourself is, which electrode is doing the work? And what I mean by this is, which electrode is moving the proton, or aka the positive charge? So just keep this in mind. If the tested electrode, so the unknown electrode that we're going to test the potential value of, or the potential difference of, if that electrode is the one that's moving the proton, it is doing work. It is the one that's carrying the current. And since there is work being done, the work done will be positive, and hence the potential, or aka the standard electric potential that we get, will also be positive. Now, if the tested electrode receives the protons, or aka the current flows into that tested electrode from the hydrogen electrode, it is not doing work, and instead the hydrogen electrode was doing the work. So the work done for this tested electrode we're trying to, measure is negative, and hence the potential that it has done is also negative. Bring back to our two examples over here. For the first one, you see the positive test charges, or just call them the protons. They're traveling from the cathode, which is the hydrogen electrode, to the zinc electrode. And if you look at the zinc electrode, it's receiving those positive charges. It is not doing the work. And therefore, since no work is being done by the zinc, sorry, I can't speak anymore. For the zinc electrode, work done is negative. Hence, it has a negative potential. And this is why we have a negative potential for zinc. Look at here. And for our second example here, hydrogen copper. So, you see, now we have the copper that is actually transporting the protons. And since now the electrode that we're testing is actually moving the protons, aka it's actually like carrying the current in a sense, it is doing work because it's actively sending out those protons into the hydrogen electrode. So since now the copper electrode is doing some work, the work done will be positive, and hence the potential is also positive. And if you look back here, it does have a positive potential. And this will be the way that I explain this entire question. I hope it's correct, and I'm not really sure, but my explanation does work. So yeah, if you want to take that into account when you are calculating some questions, please do. Or, just ignore my explanation, that's also fine. And I'm actually gonna fall asleep right now because I don't know. But anyways, you're welcome for the explanation.